Okay, here's sac205 problem 3. Give you a chance to pause this thing and read it. I'll pop in a little sketch there. Got a negatively charged particle moving distance d rightward in, well, I should say eastward. In an eastward directed electric field. Of course, there's going to be a westward force on that negatively charged particle, since the force on a charged particle is in the opposite direction of the electric field when the charged particle is negative, has a negative charge. And they want us to get the change in the potential energy of the object. Now let's see, there's going to be some work done on this object, and we can say the work done on the object is the negative of the change in the potential energy of the object. So we just need to find the work done on it, and that which we're solving for, the change in the potential energy, is just the negative of the work. And of course, work we can calculate as force times distance. It's actually the dot product of the force and the displacement vector in a case where they're both constant. And in this case, F and D are in exact opposite directions. So F dot D usually means FD cosine of theta. In this case, theta is 180 degrees. Cosine of theta is -1. Or, if you understand they're in exact opposite directions, the dot product is just the negative of the product of the magnitude. So delta U in this case is negative of negative F times D, or just F times D. Where F itself, magnitude of our force vector, is the magnitude of the charge times D. I've already taken into account the fact that the force is to the left. I don't want to include another minus sign in there, as I would if I included the algebraic sign of the charge. And then that's Q times E is the force in magnitude. So I got QED there, and I think I'm in a position to substitute the values with units, so let's do that. That's 296 nanometers times 10 to the minus 9th, so times 10 to the minus 9th coulombs, and then times E, 25,400 newtons per coulomb, and then times the distance that the particle was moved, and that's at 0.654. The distance that the particle did move, meters. So delta U, substitute those values into the calculator. A couple of multiplication symbols in between. I get 4.917 times 10 to the minus 3 joules, or everything was given to 3 significant digits, so we'll round that off to 3. Delta U, 4.92 times 10 to the minus 3 means milli, so I'll call it millijoules, for the change in the potential energy of that particle. Before I stop that one, I want to address the question, why would the thing ever move rightward under the influence of a leftward force, if we're looking at it from above, or why would it ever move eastward when there's a westward force on the particle? One, there could be another force not shown. Maybe somebody's got a hold of that charged particle, or it's on the end of a glass rod and they're just applying another force that's not shown. Or if it is a free particle, it could simply have had an initial velocity in that direction. When it was at this point, it may have already had some velocity in that direction, much like an object which is thrown upward. It goes upward even though the only force acting on it is in the downward direction. But the main issue here, find the change in the potential energy, and we've done that, so that wraps up problem 205.